Shri Sai Ram. Welcome back to this session of the study of coordination compounds, where we had seen the Werner's theory, certain important terminologies that come into this, and we had also seen how to name these compounds, where we studied the nomenclature. We had some formulas, we gave its name, we had some names and we wrote down its formula. And there was a small homework towards the fag end of that lecture. So, let us first see the answers for that and see if there is any discussion to be done for those answers. So, starting with the first homework which has been present there. In this part now, we have given names and then you were asked to write down the formula. First one, tetraamine, 4 amine groups are written there, diaqua, cobalt. As you all know, the central metal ion should be written at the start of the square bracket. And here the counter ion is chlorine, so that chloride has been written. Why it is Cl3? Because cobalt is in +3 state, it is given in the question. Amine and aqua are neutral ligands and therefore, it is written as Cl3 outside to balance the valency. Similarly, second one, potassium tetracyanonickelate. Here the counter ion is the positive ion and this is a negative complex, and that is why that ATE is written, nickelate. Third one, tris ethane 1,2 diamine, where you see En is in 3 numbers here. Cl is outside, that is basically balancing the +3 charge of chromium. Similarly, the next one, platinate, because it is a negative complex, you can see a charge there. And here there is no counter ion, it is just one full complex, and that is why you are able to see the name written in at a stretch without any gap. The fifth one, dichlorido bis ethane 1,2 diamine. So, Pt, platinum is written as the central metal ion, chlorido Cl2 di it is there, En and it is bis, so therefore that is also twice, and that nitrate NO3 twice is because to balance the +4 of platinum. Remember, Cl2 inside is balancing the -2 charge, whereas the other -2 should be balanced by NO3. Now, the last one, now this was something which I had told you that it is a little tricky, because this type we hadn't discussed outrightly when we were doing the discussions also, where iron is in +3 state, which is given very clearly, and the hexacyanoferrate which is there is seen to be the other part of this, and they are very clearly given that iron here is in +2 state. So, in this +2 state of iron which is already given, it means that for this condition to be stabilized, iron here is in +3, this is already given to be +2, and we know that Cn is -1. There are 6 Cn, so therefore the total negative charge will be -6. Now, +2 and -6 will be equal to -4. So, this part the overall charge is coming to -4, this part it is coming to +3, and from now it will be a regular balancing which takes place. So, how do we do that? This is the crossing that we tend to do. Therefore, the formula will be Fe4 in the brackets FeCN6, and then this will be thrice. This is how you are getting the answer for the sixth one which has been shown there, which is nothing but Fe4 FeCN6 thrice. We will see the next set of compounds now, which were you were given the compounds and asked to write the name. Hexamine cobalt 3 chloride. How did you write it as cobalt 3? Because amine is a neutral ligand, Cl is a negative one, and in total there are 3 negative charges. To balance that, cobalt has to be +3. Similarly, the second answer is quite similar. The third and fourth are similar in the sense that the counter ion is a positive ion, whereas the complex ion is a negative ion. So, therefore, balancing those parts, we have iron as +3 and it is written as ferrate. That 8 is because any central metal ion, if it is written in the negative complex, we end the name with ATE. Similarly, in question 5, we have it as palladate because it is ending with ATE since it is a negative complex. The last one, if you see there, diamine, because 2 amine groups are there, chlorido, then NH3 actually is amine group, but one of that NH3 is replaced by CH3 and CH3 is called as methyl. We know this in the organic chemistry. So, methylamine here is the ligand, to that platinum is present and 2 chloride, because one Cl is inside, one Cl is outside, all others are neutral ligands, and therefore, to balance the 2 negative charges you have platinum in 2 form. So, these were all the nomenclatures that we had seen in the earlier parts, and this was the homework that you had done. I hope most of you would have done all the answers correctly. So, with this background now, let us see the next parts of this coordination chemistry, where we will deal about the isomerisms that are being present. So, in the first place, let us talk about the stereoisomerism which is being presented. So, what is stereoisomerism? Stereoisomerisms are those compounds where the structural and molecular formula will be same, but their spatial arrangement will be quite different in nature. In the stereoisomerism, the compounds will have the same molecular formula and structural formula, but a different spatial arrangement will be seen. Now, this we have actually seen in the first year organic chemistry, where we had examples like this. If you remember, this was called as cis-butene. Now, what is this cis-butene? There are 4 carbon atoms and the CH3 groups are on the same side across the double bond. We had called these as cis, and similarly we had trans system also. So, how did we name that trans system? So, H was at the top, CH3 down. So, basically across the double bond, if the same groups are on opposite sides, we had named it as trans system, and this was trans 2-butene. With the same basics of this, in the stereoisomers of coordination compounds, we will be studying now, where instead of a double bond, we will consider the central metal ion to be the center part. And to that central metal ion, if they are on similar sides, we will call it as cis. If they are on different sides, we will call that as trans. Now, this is part of geometrical isomerism. There is another part which is optical isomerism, which we will see through this system. So, just going through that part now, the structural isomerisms where geometrical and optical isomerisms are present. In the first part as geometrical isomerism, in the bracket you are able to see Mx2L2. What is that? M indicates the central metal ion, X2 indicates one of the ligand, L2 indicates another type of ligand. Now, these are all called as heteroleptic ligand. This we had studied in part 2, where heteroleptic indicates 2 different types of ligands. So, in the first example you can see that Cl is present on one side, NH3 on one side, whereas in the second transform you are able to see that Cl and NH3 are opposite to each other. So, this will give a 3-dimensional variation in this compounds. What are the use of this compounds? The first compound cis is actually called as cisplatin, which is a very good agent that is used in chemotherapy in curing various types of cancers. So, this cisplatin is seen of a large importance in the medicinal field mainly. Similarly, the other geometrical isomerism, this is an octahedral structure where you have in total 6 ligands being present. And how do you determine which is cis, which is trans? You are able to see that a Cl in cis is actually present along the same side, whereas in trans it is present along the opposite sides. If you see the nomenclature there, it is Mx2L4, which indicates that one of the ligand is in 2 in number, the other ligand is 4 in number. What does the positive charge indicate there is because NH3 there are in total 4 and we know that they are neutral ligands. Cl there are 2 and 2 indicates -2 total charge available, and cobalt here is in +3 state. So, if cobalt is +3 and Cl is in total -2, the overall charge will be +1 in this cases. So, this is about certain examples of geometrical isomerism that we are able to see in these cases. So, what is important to be understood here is that a central metal ion will have ligands present all along, and if they are on same side, it will be called as cis. If they are on opposite sides, it will be called as trans. So, moving further now, let us see some more aspects of this geometrical isomerism, where now we have this Mx2LL2. Now, what is this LL2? It means that They are didentate ligands. What are didentate ligands? Didentate ligands are those compounds which can donate two pairs of electrons from a particular molecule. So, what is the importance of these type of systems is that they are able to give electrons in such a way that each molecule can have two centers of electron donation. So, what is the example that you are able to see there? It is showing you something like cobalt being in combination with Cl, also with NH2 it has been present. That En which is shown in short form, this is the completely long version of this compound. So, what is happening here? There are 6 centers which are donating electrons. Now, a cis indicates that the one of the types will be near to each other or near the similar parts, whereas the trans indicates that Cl will be opposite to each other. So, if you see in the difference that has been shown there, Cl is present just beside each other, whereas in the trans form Cl is present on either sides. So, to make it more simple as such, if you have to use the 3-dimensional space in this case, if I use my hand as a plane of the system, if I use this as a plane of the system, cobalt is present here, and if when I consider a trans system, this cobalt at the center will have 4 ligands on this plane as a square planar. The 5th ligand is at the top, the 6th one is at the bottom. So, if the Cl is present at top and bottom, we take it as trans because they are opposite sides. Cis can either be on the same sides on one side or it can be on top and one of the sides. This is how we determine whether it is a cis isomer or trans isomer in nature. So, this is about the geometrical isomerisms that are being present with respect to coordination compounds. Let us see the further parts of this stereoisomerism which is there now, which is classified as FAC and MER isomer. Now, in this case, the type of compound required is MA3B3. What is this A3B3? Once again, A indicates one type of ligand, B indicates another type of ligand. What is the difference that you are seeing in these two? In FAC isomer, the ligands are present along one direction or on one side, whereas in the MER isomer, you are able to see that one NH3 is at the top, another NH3 is at the bottom, and the third NH3 is actually on the plane. So, such systems where the ligands are present on either sides of the plane, we call them as MER isomer. And if these ligands are present on the same side of the plane and maybe one side of the octahedral system, we can call them as FAC isomers. So, this is one of the examples that is being present for this compound. This is all about the geometrical isomerism which is present for the coordination compounds, and the next set of compounds which we are going to study are the optical isomers. Now, what is optical isomerism? This again we have studied in the haloalkanes and haloarene system, where we have terminologies like dextro-rotatory system and levio-rotatory system. So, in this cases, a dextro-rotatory system is denoted by D and levio-rotatory is denoted by L. What is this basically? Suppose if I have a compound with me, maybe I have taken it in a rectangular system, and if I pass light through this. Now, which type of light? Not all types of general light. It is this light which has a particular sort of wavelength, and if that wavelength of light is passed, if it is showing optical isomerism, it is seen that it may deviate the direction of light towards right or left. If it deviates towards right, we call it as dextro-rotatory. If it deviates towards left, we call it as levio-rotatory. Now, this is only possible if the compound is having a chiral atom in that. And what is chiral atom? These are non-superimposable mirror images. So, what do you mean by non-superimposable mirror images? It means that two mirror images cannot be superimposed on each other. So, such type of compounds can show this optical isomerism, and the theoretical study of this optical isomerism is pretty less, because all these compounds need to be individually studied for their properties, whether they can move their light towards right side or left side, or will they not at all move the light in the system. So, in the example that is given for you here, you are able to see that in this case the ligand that is used is a didentate ligand En, which is ethylene diamine, where the light that is passed through the system can move the light towards right side or left side, indicating that they can form dextrorotatory or levorotatory systems. Similarly, another example where they have used two didentate ligands, two unidentate ligands, and this sort of system can show a dextrorotatory or levorotatory depending on the direction of the light seen once it is passed through the compound. Now, in this, be very clear that while in geometrical isomerism we had a proper demarcation to distribute itself between the cis isomer and trans isomer, in optical isomerism it is very difficult to tell theoretically whether this one can be dextrorotatory or it can be levorotatory. This is only possible by practical analysis that we tend to do, and that is why from the examination point of view or the textual point of view, you are given minimum examples regarding these compounds. So, this is about the optical isomerism and geometrical isomerism, which is together called as stereoisomerism in the study of coordination chemistry. Hope you have understood this well. Thank you. Sai Ram.